We're going to cover mostly today theoretical properties of the Lasso. I just wrote up a quick review of what we talked about last time on the board. I really don't know how long it's going to take us to go through the Lasso theory. I suppose we could either go more quickly or more slowly through some parts, because we could either try to prove some parts or just leave them to the notes. So we'll see how we go. If we get to the end and we have time left over, I guess we can do a couple things. One is I can prove this uniqueness claim, which we talked about last time but didn't prove. Or I could kind of freeform a bit of inference, talk about inference a bit that people do with the Lasso. This is kind of more recent work. The last couple of years, people have started looking at this. So if we have time left over, we can take a vote. Just to let you know what happens next week. Next week, we have a review session on Monday. I think that's on the schedule. And then Wednesday is the midterm. People apparently are nervous about the midterm. I haven't heard that firsthand, but the TAs have been telling us that people have been emailing about the midterm. So let's talk about it a bit now. We're going to have you prove the Lindenberg CLT on the midterm. And you're going to try to do it under the weakest conditions possible. Actually, just try to get you to prove new results. I'm kidding, of course. That's not the midterm. So the midterm is not going to be that challenging in the sense that it's going to be easier than the homeworks. We aim to make the midterm easier than the homeworks in this class. The list of topics, we wrote down a list, Larry and I, earlier. We'll have the TAs email that out or put it on Piazza. It's just going to be on the stuff that you covered so far. We're also going to do practice problems in the review session, or we'll just go through some problems on the board. I figured we could. OK, review session's mostly question and answer, but we'll have a few practice problems as well. So come on Monday with questions you have. Like I said, the midterm's going to be easier than the homework. So you're not going to get asked a question that's longer than a homework question. That you wouldn't be able to do that in 80 minutes' time. Questions about the midterm? Any concerns? Yeah.
Is it possible to post like 3 or 4 sample questions so we know the difficulty level?
We had a practice from last year. We might put that up from last year, something like that.
I have to admit, I tried to find it and I couldn't find it, but maybe Ryan will have better luck to find it.
OK, yeah, we'll be able to do that. So we'll post them in advance of Monday's. We'll do the following. We'll post them in advance of Monday's lecture, say on Friday. Try them over the weekend. And then Monday, if you can't solve a few, we can go through them. Yeah, Kevin. Yeah, should we do that?
Yeah, sure.
OK, sure. One sheet, front and back. As small a font as you want. Yeah. Due date next homework is like end of March, mid of March?
It says it on the...
I can't remember. It's not for a while.
Oh, yeah, there was a typo. So I think on the web page it correctly says March 20th, but I think on the assignment we put March 2nd by accident.
OK.
So add a 0.
The website's correct, yeah.
Can we release all the homework answers of homework 1 and 2 before the meeting? Also lecture video.
Sorry, what was the question? Can you?
The answers for homework 1, 2, and the lecture videos before the meeting.
So the solutions to homework 1 is out.
Yeah. Okay.
They're on Piazza. Homework 2 should be out soon too. The lecture videos, yeah, they'll come up soon. There just was a bit of a delay, but that'll be up. Other questions? OK. Yes?
When did you say the list of topics would be out?
This afternoon. We can just email it out this afternoon. It's basically everything up until today, including today's lecture. But we didn't like the notes on clustering is very long. The notes on non-parametric regression was very long. So we're not going to expect you to know everything in those set of lecture notes. So just the things we talked about in lecture. And then we'll just summarize that in the...
Yeah, I would say if we didn't talk about it specifically in the lecture or in the homework, you don't have to worry about it for the test.
And including Sparsity?
Yeah, we didn't talk about everything here. So, I mean, the stuff we focused on, like this stuff, for example, stuff I'm writing up on the board. Oh, these lecture notes are not as long as the other ones. So, yeah, these are like 15 pages. The other ones were much longer. So, other questions? OK. So just to tell you what we did last time. we talked about the Lasso problem. We talked a bit about subset selection as well. We saw that actually that subset selection was optimal in some sense for prediction when we compare it to the oracle predictor, which knows the set of relevant variables ahead of time and just performs regression on those variables. Its risk was worse by a factor of log p than the oracle, and we saw that that was optimal from subset selection. Subset selection is not computable in practice. It's also a lot harder to understand. People spend a lot more attention thinking about the Lasso because it's computable and we can understand it better. So it's become much more of a popular topic for sparse regression. Here are some of the properties we talked about last time. The fitted value in the Lasso problem is always unique. So if I were to solve this problem, which looks like least squares plus an L1 penalty on the coefficients, I get a unique fitted value no matter what x is and no matter what lambda is. The solution itself can be non-unique. That can happen. So what's an easy example where you can convince yourself it's non-unique? Suppose you had two predictor variables that were exactly the same. So I took two columns of x and they were exactly the same. Suppose that one of them was active at the solution, so I assigned a non-zero weight to one of them. How could I get a non-unique solution?
Split the weight in half and
Right, I can just divide the weight equally between, say x1, x2 exactly the same. If I put full weight on x1 or equal weight on the two of them, that has the same L1 norm in either case, and they both produce the same fit. So they're both going to be the exact same in terms of the Lasso criterion. But we saw that even if the solution was not unique, if I have any two solutions of the Lasso, then they have to agree on their signs in every component. So in particular, if I have any variable that's active both in, say, the Lasso solution beta hat and active with respect to a different Lasso solution beta tilde, then they both have to be either positive or negative. So that's good. It means we can at least interpret the signs consistently of the variables that we see. Furthermore, it's unique when this matrix X has what we call a general position property. And that means that its columns don't have trivial linear dependencies of lower order. So the precise definitions in the notes, you can think about it as follows. If I give you any subset of k columns of X, where k is smaller than n and p, it's some smaller collection of columns, then if I take their linear span, that cannot contain a k plus first column. The precise definition actually is just slightly different than that, but it's almost the exact same. So the linear span of any subset of k columns can't contain a k plus first column. That's a very weak condition on X, and it can be true even when p is much bigger than n. And the notes actually argue that if p is anything and n is anything, and X has a probability distribution that's continuous, if X came from a continuous probability distribution, then this happens with probability 1. So we basically get uniqueness very often in practice. And the last thing we saw to do with these kind of basic uniqueness properties was the form of the Lasso solution when it is unique. When it's unique, we saw that that means that there's some subset of variables A, we call this the active set, for which beta hat's 0 outside of A. And on A, it looks like this. And this means the columns of X that are in the subset A. And when it's unique, this matrix is always invertible. It's one property of the Lasso. And so we're really just doing regression on the active variables. That's what this term is. So that this term itself, without the second term, would be regression of y on the active variables. But this is performing some kind of shrinkage. So we can see from this expression that there's a bit of bias that the Lasso introduces into its estimate of the active coefficients. And aside from these basic properties, we talked about the LARS algorithm. Stands for least angle regression. It's an algorithm for computing the Lasso solution path, and we saw that there exists a set of what we call knots, lambda values, such that the solution is linear in between those two knots as a function of lambda. So if I knew its value at lambda k and lambda k plus 1, I know its value at every lambda in between. It's just a linear function of lambda. And it's also continuous over lambda. So the solution doesn't have any jumps as we change lambda. And each of these lambda k's are very special. They mark either the entry of a variable into the active set or deletion of the variable into the active set. So as we start lambda at infinity, the active set's empty because the Lasso solution is 0. All of the coefficients are 0. As we decrease it to lambda 1, that marks the entry of the first variable in the active set. And lambda 2 marks the entry of the second variable in the active set. And so on and so forth, except that some of these could also correspond to a variable moving out, being kicked out of the active set, so becoming 0. Any questions about these properties? Yeah, Kevin.
Because of the bias, the lasso isn't consistent even in low dimensions, or is that not true?
No, it's consistent. It depends what the scaling is. So, it depends on how fast lambda grows.
Oh, if I fix a lambda and only my sample size is changing.
So again, it depends on the scaling. So if the columns of x are growing in norm, then lambda should also grow in norm. And it will still be consistent in a certain regime. So there's like a classic paper of Knight and Fu, Keith Knight and Fu. I didn't actually put it in the notes. That asks about something like the asymptotic distribution of the lasso for fixed dimension. That's one of the earlier papers that studies this topic. And you can see the scaling there. I don't remember exactly what the scaling is, but lambda has to, in a kind of typical scaling, lambda goes to infinity at some rate if the columns of x also grow in norm. And you can get consistency in that regime. But if lambda is too big, you're right, I won't get consistency because I may bias myself too much. We'll actually see the lasso is consistent. I'll even prove it for you for the high dimensional case. It's a pretty short proof. Other questions?
Yeah, so I guess I know that the answer to this is probably domain specific, but how often is it the case that as we decrease lambda, we kick out variables?
It's a good question. So there's a sufficient condition that you can write down for when that doesn't happen. It's called the positive cone condition. It doesn't mean anything real. It's just a mathematical condition that ensures that we only get additions. So if x satisfies something called the positive cone condition, then there are only additions. This is found in the LARS paper. In practice, I'd say, from a completely non-rigorous point of view, if p is larger than n, then deletions happen all the time. So it's very common. So it's pretty rare that you don't get variable deletions as you move down the path. Even like if suppose I generated the entries of x from a normal distribution with mean 0 and variance 1. So in the population they were uncorrelated. So it's pretty innocuous. Not a lot of correlations there. If I would say, again, without any rigor behind the statement, it very often happens that if that was your design, you'd get variable deletions, even if p isn't that big. Other questions? Okay, good questions. So today we're going to talk about some theoretical properties of the lasso, and all this stuff kind of happened historically, all this stuff kind of happened at one time. It was kind of interesting. The lasso was proposed in '96, but people didn't really pay as much attention to it as they do now until, I'd say, mid-2000s. So in the mid-2000s, there was a bunch of papers on lasso theory that was really exciting, that convinced people lasso was worth studying. And there was also a separate line of papers about how to compute the lasso solution quickly. So the LARS paper was 2004, and then later papers came out. And in practice, people don't really use LARS necessarily for really, really large problems, but it's still it still gives us a lot of insight into what happens with the lasso. So like I said, all this happened at around the same time. So the papers I'm listing here, let's see, 5 papers that are all 2004 through 2006, and there's a ton more that I have left out as well. And we're just going to kind of give a survey of some of these results, and then we're going to actually prove one of them. So I'm going to make some assumptions here just because it's simpler to write them down. In the papers, you'll find that actually the conditions they pose are actually a bit weaker than what I'm writing down. But let's assume that we have a linear model of this form, a true linear model of this form. So just, I'm going to sound like a broken record, but I'm just going to repeat the fact that this is, probably suspicious in practice. I'm assuming that x is fixed, and I'm assuming that the errors are IID across the observations, right? That we've talked about this a couple times at least. Suspicious in practice, but it's a tractable setting to think about theoretically. So it's pretty much the assumption people make when they think about the lasso or high-dimensional regression in general. This assumption, normality, could be relaxed. So the assumption that epsilon is normal here is not really as crucial. If you look at the papers, then they do it for different distributions. Sub-Gaussianity, for example, is a broader class of distributions. OK, so y is random. We're assuming that this is the model that we're observing. And we're going to also assume this is just for scaling. This assumption itself doesn't really matter at all. We could repose it in a different way, but this is just for scaling. We're assuming that each column of x has norm root n for all the predictor variables. Okay, if we didn't want to assume this, then we'd have to assume something about the variance shrinking. If we assume that the columns of x had norm 1, then we'd have to assume that the variance was shrinking. But that this is, this particular assumption is, the way I wrote down is not so important. So the first result that came out on the lasso stated a bit differently than this, but people have rewritten it in various ways, and now it's been distilled as something very simple. And this is the one that we'll prove. Is what I would call the basic result for the lasso. Another word for it is a slow rate bound for the lasso. And it says the following. If we choose lambda on the order of, for this problem, square root of n times log p, then the lasso has the following mean squared error when you look at the fitted values. So this is the difference between the lasso fit x beta hat and the underlying mean squared error. It looks like the following. This means that it goes to 0 at the following rate. Or, sorry, it's bounded in probability by the following quantity. And there's a sigma here. OK, you guys know what this means, right? Bounded in probability. We learned that in 705, and we talked about it the first lecture as well. OK, so what does this tell us? This tells us that if the norm of the underlying coefficients, beta naught, if this were to go to 0, or if this would just grow slowly, so if this was little o of root n over log p, then the lasso would be consistent. Right? So if this grew slower than root n over log p, then their product would go to 0, so this over the mean squared error. That's the first basic result for the lasso. What's the amazing part of this result? There are no assumptions on x. So this is true for any sequence of predictor matrices. Let's see. Yeah, let's compare this now to, well, actually, no, we'll compare a little later to the result we learned for subset selection. But I'll write down the result for subset selection so that you're reminded of what it looks like. We had x beta hat minus x beta naught squared this was, it was a little different because this was an expectation, but that's not so important. This was bounded by, it was S naught sigma square root log p times S naught, where this was the number of underlying variables that were truly active. So if I were to divide by n, just to put this in the same scale, it looks like that. So here we're not actually assuming sparsity. In this result, there's nothing assumed about sparsity. So all we assume is a form of weak sparsity, which means that we're not assuming that beta naught itself has a small number of non-zero entries like S naught. We're just assuming that its L1 norm can't grow too large. In fact, it can't grow any larger than this. But even so, let's just try to compare these two results. What do we notice? So this is nowhere near as sharp as that, right? Because I'm dividing by root n here, for example, and then I'm dividing by n. So these are really different in terms of their rates. So we're not getting close to what subset selection gets. We don't have any notion of S naught here. We've replaced S naught by this quantity, which is not counting the number of non-zeros in beta naught. It's actually summing up its L1 norm. So that's probably going to grow bigger than S naught. And here we have root log p over root n. There we have root log p over n. So both of these make no assumptions about x. This one's a lot worse. We're going to see we can get very close to that once we start making assumptions about x, but I wanted just to make that clear first. Yeah?
Can't we use equivalence of norms to get some notion of sparsity in here? Because if we use equivalence of norms as for the L1 norm and L0 norm, we can impose the L0 norm and at least get a lower bound or an upper bound. Because the L1 and L0 norms are equivalent, and then you have sparsity built in there as well.
So the equivalence between norms is not something that scales favorably asymptotically. Equivalence between norms for any Euclidean space, like what's the equivalence between the L1 norm and the L2 norm? It scales with the number of entries that are non-zero. So that's not something that's going to really help us. I mean, we could say something like, let's suppose that each of the coefficients here had a maximum entry t. Then this would be less than or equal to t times S naught, right? So you're right, we could try to put on that scale, but then it would be kind of thinking about the same problem, which is how big does the maximum entry of beta naught get? So we'd see we have to replace similar restrictions like this. It's a good question, but I think actually the thing that bothers us more is this. Right, so we're on the squared error scale. This is converging at the rate 1 over n times root log p. This is 1 over root n times root log p. It's very, very different. Yeah?
I have a question about the result. The one I'm familiar with, which is the Greenstein-Ritov, has norm L1 squared in there. Whose result is this?
That's interesting. So this is a restating of Greenstein-Ritov's result, but that's proved in the Bielmann-Van de Geer book.
I guess the difference is Greenstein-Ritov are assuming nothing, whereas this is assuming normality and constant sigma and stuff like that, right?
Greenstein and Ritov have to assume some kind of error model, right? Oh, so their x is random, is that right?
X is random and there's no linearity, there's no
I see.
normality.
Yeah, that's probably the difference. Yeah, so this is for fixed x, but any fixed x.
But are they assuming here that the linear model is correct?
Yes, yeah,
Okay, that's the other big.
yeah, that's true. That's here. Yeah, so the reason I chose this is because the proof of this is like 6 lines, so we'll go through this after I state all the results. Then comes the more complicated results, and there are a lot of them out there, and so I've chosen to mention 2, or describe 3, sorry, that have to do with consistency. Let me see. I'll leave that up here, and I'll just erase this stuff. So just keep this in mind, this model in mind. It's in the notes too. And here's what I would call strong results, but they're only stronger because we assume more. So you might hear these called strong results. In other words, some people call these fast rates for the lasso. They all assume more. So here's the first one, I'd call these compatibility results. So if we're willing to assume something about the variables in X, then we can get stronger mean squared error bounds on the Lasso fit. And the first assumption we might think about making is compatibility. And that's saying that if we knew, suppose we knew the underlying support. So these were the set of truly relevant variables in the population. And again, we're going to use the notation that S naught is the size of S, just like we did there for subset selection. Then compatibility is the following. We say X satisfies the compatibility condition with constant phi. It's called the compatibility constant. If the following holds. The norm of x beta squared has to always be larger or equal to phi naught squared divided by S naught times the L1 norm of beta once we restrict it to S for all vectors beta such that the L1 norm of beta outside of S is no more than 3 times the L1 norm of beta inside of S. Okay, so kind of a mouthful. That's the compatibility condition. I should be careful saying this because we're being videotaped, but why do we write this down? It's because this is the thing you need to prove the result. If you write down the proof of this, we'll see that at some point you need to assume this, and so that's what you assume. And it gives you the fast rate for the lasso. It's actually connected in many ways to other conditions. I think some of them are more clear. So I'm not really trying to dump on it. It's just that I don't think this is, you wouldn't think of this as being a property of a predictor matrix that you think would be desirable, for instance. But if X satisfies this compatibility condition, which roughly speaking says that something like the eigenvalue of X, the lowest eigenvalue of X when we restrict ourselves mostly to the set S, has to be bounded away from 0. So why is it saying that? It's saying that because we're looking at variables, coefficient vectors that are mostly concentrated on the set S. Because outside of S, they have a small L1 norm, so most of their weight is inside of the set S. That's what we're restricting ourselves to. And now we're looking at this quantity. It's not really this, right? But this is going to be approximately equal to this because, like I said, most of the weight is inside of S. And we're actually asking this to be bounded away from 0 by something times the norm of beta S. So that's kind of like a lower eigenvalue restriction on X on this matrix XS transpose XS. That would be more clear if this was an L2 norm, actually, or an L2 squared norm. And that's actually going to be the next condition we write down, which is called the restricted eigenvalue condition. But the intuition is that this holds when the variables inside S are not too correlated, because then their lowest eigenvalue, the lowest eigenvalue of XS transpose X, is kind of buffered away from 0 in some way. So yeah. Yeah, the notes are right. Then I'm sure I just wrote that down wrong. Yeah. Thanks. Okay, so what's the result we get if we're willing to assume this? We get some very nice results. So if the variables aren't too correlated among the variables that really matter, the ones that are truly active at the population solution, then if we choose lambda, which is of the same order as before, root n log p, we get two things. I'm going to write these backwards, actually. I'm going to write down the first result here and the second result all there, down there. So the first thing we know is actually that we get consistency in the coefficients themselves, not in the mean, the fitted values, but in the coefficients themselves with respect to the L1 norm, so that the L1 norm of the Lasso solution beta hat minus the true coefficient vector is bounded in probability by sigma root log p over n times s naught over phi naught squared. So if we assume that the number of variables that were truly relevant in the population was a constant, so this was a constant, and we're able to guarantee that the compatibility condition stayed away from 0, then we're saying that it's consistent at the rate log p, root log p over n, for example. So we can actually estimate the underlying coefficients very quickly under a pretty substantial assumption, right, that there's not much correlation between the variables inside S, that true set of relevant variables. The other thing we get, so remember that this was for subset selection. I'm just going to write the Lasso result underneath here so you can compare. So this is the Lasso under compatibility. We get that this looks like, so this should have been a sigma squared. Everywhere there's a sigma should be a sigma squared. Oh, I suppose not. It's a bit funny. Maybe I have a typo in the notes. Anyways, this is a sigma squared times, see if I can write it like this. Same thing, S naught sigma squared log p over n times 1 over phi naught squared. So it really comes very close to goodness, I'm making lots of typos. That for the subset selection results, I think I just wrote that as root log p for no reason. In the notes it says log p, right? Yeah, it was log p. So we have a log p risk inflation from the oracle risk, which is this. So for the Lasso, we get the same scaling. So this is maybe comforting. The only difference between the rates are that, well, there's a minor difference. This one's in probability, that one's in expectation. For the Lasso, we also have this compatibility constant here. This is something like a lower bound on how correlated the truly relevant variables can be. If this gets really small, then this degrades. So there's a lot of conditions that make this that are required to make this true versus nothing that make it true for subset selection. But at least we have a way now of at least we have an instance that we know concretely the Lasso performs just as well as subset selection in terms of prediction error. Okay? Any questions about that? Yeah?
How often does the conditions come true as a compatibility result?
It's a good question. So often people couple these results with a result for which x is random. And they say things like, if x is random and comes from some distribution, then this holds with high probability. And so, for example, if x had IID entries that were normal 0, 1, then this is going to hold with high probability. So under some random models of x, these things hold with high probability. I think this is still true. It was true at least a couple years ago. So these results are all, in a sense, so these conditions are all in a sense, they depend on n and p as well, right? This has to be, So if I want to apply them, I have to know this holds for a sequence of matrices X as n and p grows. This kind of thing always has to happen. That's what I need to assume in order to apply this result. So people didn't know, at least as far as I can remember from a couple of years ago, or a year ago, deterministic constructions of matrices that made these hold for arbitrarily large n and p. So we didn't actually know something some deterministic construction of a matrix X that always satisfied the compatibility condition. That was true of something called the restricted isometry property, which is very similar to this. And so people were actually trying for a long time just to find deterministic constructions of matrices that satisfied this, like I said, over the sequence of n and p, but they were failing. And the only results that they relied on were these random results that said that if X came from some distribution, then this happens with high probability. So again, that wasn't a great answer, but I mean, this is pretty restrictive is the way I would think about it. If the variables are weakly correlated, this is probably going to happen, but it's not going to happen if the variables that contribute in the true population model, right, S was the support of the underlying coefficient vector. If they're correlated, this is not going to happen. Yeah, Kevin.
So if I assume that there's not actually sparsity, but a lot of coefficients just rapidly decay,
Mm-hmm.
do these results also break down?
Yeah, it's a good question. This one doesn't, right? This one didn't have that restriction. These fast rates don't either, but I think you have to be a little careful about how you state them. So they instead of assuming strict sparsity, one could assume weak sparsity, which is either sparse with respect to the L1 norm, like this is small at the true coefficient vector, or LQ sparsity, where Q is less than 1. Like I assume that the Q norm of the true coefficient vector is small. Those results are out there. As far as I remember, they under maybe comparably restrictive assumptions, they reproduce these results. Do you have any other answer to that?
I think it's pretty much the same.
Yeah. Any other questions? Yeah.
So the elastic net does rules selection. So if you assume that model, does it, and do the same analysis, does it get rid of that independence assumptions for X?
This? No, definitely not. So this is pervasive for the elastic net as well. The results in the elastic net aren't very different either. So I have to say I haven't spent as much time looking at the theory for the elastic net as the lasso, but there's a lot less of it too. It's a good question. So just to maybe fill the rest of the class in case they don't know what the elastic net is, the elastic net looks like this. So instead of using an L1 penalty, we use a convex combination of L1 and L2 squared penalties in the least squares criterion. And what this does, which is what was mentioned here, is it tends to group the contributions of correlated variables towards each other. So if I have a bunch of correlated variables, the lasso, because it's kind of an informal statement, it might pick out one of those variables to put in the active set. The elastic net tries to bring those variables all in the active set. And that's because if we think about spreading out the contributions over all the correlated variables, then that's what's favorable when we add this little bit of L2 norm, rather than just putting in the contribution for one variable. That's, I think, the reason why people like to use it in practice. That and other reasons, it's kind of favorable in some sense. Computationally, maybe sometimes to use the elastic net. But theoretically, I don't think there's much of a difference. There's not like a strong difference in the theory. Good questions. Other questions? Okay. So there's one other condition that I want to write down called the restricted eigenvalue condition. So there's compatibility, there's this one, restricted eigenvalue condition, there's restricted isometry property, there's restricted strong convexity. There's a lot of conditions out there. There's one paper that tries to relate all of them. I think it's linked in the notes by Peter Boelman and Sarah Vandegeer. And their book, there's a book by Peter Boelman and Sarah Vandegeer that also gives a nice summary of all these results and how they relate. But I just thought I'd pick two of them, the two strong results. So restricted eigenvalue condition is similar to compatibility but it's just stated a little differently. And that's the following. Just the norm of beta squared. This has to be true for all subsets J such that J has size equal to whatever the size of the true active set is. And the same kind of cone condition holds. So what are the differences between these two? Well, the one difference is that the compatibility result is a property that has to hold for the true active set in question. Right? We're asking that on the set S, if we have something that's mostly concentrated on that set S, then we kind of lower bound something like the eigenvalue of x over the set S. The restricted eigenvalue condition is applied to all subsets that are of the same size as the true active subset. So in a sense, this is something you could actually check if all you knew was the size of the active variables. This isn't, right? Because this depends on the variables themselves. So if I told you there are 10 true variables in the population, then this applies to every subset of variables of size 10. So maybe it's just a little bit more easy to grasp, right? That this is a condition. It's still not possible to check, right? Because it requires us knowing the number of active variables, but we've removed the dependence on the active subset itself. So it's basically this has to hold for every subset of the same size as the true active subset. That's what this is saying. Plus, there's a difference here. We've changed the L1 norm to the L2 norm, and we've gotten rid of the dependence on S there again. So this is actually now really saying that something like the eigenvalue of xj, the lowest eigenvalue of xj transpose xj has to be bounded away from 0 for any subset j whose size agrees with the size of the true active set. It's not quite that again because beta can be non-zero outside of j, but it's limited to how big it can be outside of j. So this holds when every subset of variables of the same size as your true active set. So for example, if that was 10, every subset of variables of size 10 are not very correlated. It's a very strong condition. I think in the notes I even give a little bit. Right. So in the notes I actually have a little argument here that says that this actually implies the compatibility condition. So if you were to assume the restricted eigenvalue condition, it's an even stronger assumption because actually you can see it implies this. Just a little argument in the notes. But like I said, for the reasons we already stated, that one might be a little bit easier to grasp. And if we assume that, then with the same scaling for lambda, we get a very similar result, except this is n log p. The result is in 2 norm. So this is the one that people use if they want to prove consistency of the Lasso estimate, the coefficients themselves, but an L2 norm. The result for this one was an L2 norm. The result for this one was an L1 norm. OK, that's a summary of Lasso consistency theory. You can find much more than that in the literature, and I've given some references, but these are maybe 3 of the main results. So take-home message is Lasso does pretty well in terms of prediction error. I erased the weak rate, the slow rate. Does pretty well. We know it's consistent under very general conditions. In order to get something comparable to subset selection, which is close to the oracle, we have to assume that the correlation that we're observing between, say, some relevant set of variables at the population level is small. Otherwise, these bounds don't apply, the ones that I derived here. Although there's some recent work that shows that tries to analyze the Lasso under correlations, and it actually shows that in some cases you can get some favorable results too. So people are interested in that now as well. Any questions? Okay, let's take a break, and then we'll come back and we'll finish. We'll do the primal dual witness method for support recovery, and then we'll see how much time we have after that. Okay, so I realized that I didn't give a joke last time, so don't worry, I haven't forgotten about that. I have a very special thing for you now, which is even better than a joke. It's a secret, and it's just going to stay between all of us. It's the secret to why Rob Tibshirani invented the lasso. No one's seen this, so you got to turn the camera off for this one. It's a secret. This is the real reason that Rob Tibshirani invented the lasso. So you can find Lasso beer in Pittsburgh, by the way. Not that I would ever encourage that kind of thing.
It's hard to find out. It's kind of sparse.
All right. So that was plenty of jokes. By the way, I showed that to Larry earlier, and he came up with a whole day coming up with that joke. That wasn't All right, so I realized I actually did not prove the basic inequality. I claimed that we would. So now we have an option. We have about, I think, 20 minutes left. Is that right? 25 minutes left. So we're going to talk about the primal dual witness method for constructing. It's a method of proof that was pioneered by Martin Wainwright to check that the lasso recovers the set of variables themselves. It's more than consistency. It's something called sparsistency. We can either do that in detail, like the proof of that, as well as the results, or we can just state that result and prove the basic inequality. I'm kind of more leaning towards proving the basic inequality because, like I said, it's pretty simple. Does anybody really want to see the proof of the primal dual witness method? It's in the notes, by the way, so you can go through that.
Sorry, basic inequality being the basic result?
Yes, right. Okay, well, since no one's objecting, I'll go through the basic inequality result. So let's prove it. Let's prove the basic inequality. If we're really good, we could probably do it in one blackboard. But I don't know if we'll be able to fit it. I'm deferring part of this to your homework. So it's not really one blackboard. But the part you're checking on your homework has nothing to do with the lasso. It's a very basic fact about Gaussian concentration. And then we'll see Gaussian concentration results in much more detail later. This is just a simple fact about the maximum of independent Gaussians that you're going to check on your homework. So here's the proof of the basic result. We start just by saying that at optimality, if I were to take the Lasso criterion, this is the Lasso criterion evaluated at the solution beta hat. This is as small as this thing gets by definition of beta hat. Nothing can make this smaller. So in particular, it must be less than or equal to what happens if I plug in beta naught, which are the true coefficients in the population. It's a very simple observation. And now we're going to rearrange this. So we're going to expand the square and rearrange. So let's expand the square. We get right, this minus y transpose x beta hat plus 1/2 x beta hat squared plus the L1 norm, I'm going to actually move the L1 norm to the other side, is less than or equal to the same stuff, but in terms of beta naught. Plus the difference in L1 norms at beta naught and beta hat. So nothing tricky there. These cancel. I'm going to move this term to this side. So I'm going to say that 1/2 x beta hat squared minus 1/2 x beta naught squared is less than or equal to I'm just going to move this up. What happens when I subtract this from this? I'll move that to the other side. I'm going to remember the fact now that x beta hat, right? Or rather, I'm going to remember the fact, sorry, that y, remember y is x beta naught plus epsilon. It's going to become important here. So I'm going to write this as y transpose x beta hat minus x beta naught plus lambda times the difference in L1 norms. So now plug in for y. What do we get? We're going to get epsilon transpose x beta hat minus x beta naught plus x beta naught transpose x beta hat minus x beta naught. And what is this? Well, look, we have one term that looks like x, the norm of x beta naught squared. And we also have minus 1/2 of it there. So if I move that out to the other side and move this term to the other side, I'm going to get 1/2 x beta hat squared minus x beta hat transpose x beta naught plus 1/2 x beta naught squared is less than or equal to lambda beta, epsilon transpose x beta hat minus x beta naught plus lambda times the difference of their one norms. But the reason I've done all this is because, look, this thing is what I want. This is just equal to x beta hat minus x beta naught squared. That's the mean squared error I'm trying to bound. It's a pretty simple bound I've achieved too. Mean squared error is less than or equal to the sum of two terms. So what's our strategy going to be? Our strategy is going to be the following. This term is random. This term depends on epsilon. Epsilon, we know its distribution. It's random. This term is also random because beta hat's random. But the randomness here is harder to capture. I don't know anything about the distribution of beta hat. The distribution of beta naught's of epsilon is much easier to play with. It's just normal. So I'm going to try to make lambda, my choice of lambda, large enough so that we know that we can bound this term by something involving this term. We're going to make lambda large enough so that, for example, this term is just less than that term. So we just can think about our bound being this term times 2. But I want to also make lambda small enough so that that's not going to be a bad bound. Of course, I could take lambda as large as I want. It's always going to be bigger than this part. But I want the bound to be good at the end of the day, so lambda has to be still kind of small. So we want to pick lambda to be just large enough so that it dominates this term, but no bigger than that. So how large does lambda need to be? That's a pretty simple calculation to do. which you're going to do on your homework. And it just involves studying this process. So I'm going to look at this first term. Call this term A. Look at term A. A is equal to x transpose epsilon transpose x beta hat minus x beta naught. Let's use Holder's inequality here. So Holder's inequality tells us that we can always bound the inner product of two things by the norm of one and the norm of the other. Sorry, there's no x here. Right? All I've done is I've moved the x to here. And this is less than or equal to, if I chose to use, for example, the infinity norm, one norm pairing for Holder's inequality. The infinity norm of x transpose epsilon times the one norm of beta hat minus beta naught. It's always a funny pairing the way it happens. If you were in convex this morning, we saw this too, right? Because we talked about dual norms. We talked about it just for general dual norms. So A is smaller than or equal to this. This is complicated. I don't want to deal with this because beta hat has some complicated distribution. I don't really know much about it. Let's try to deal with this. Let's try to get a probabilistic bound on x transpose epsilon. So what is that? X transpose epsilon, an infinity norm, just by definition, it's the maximum over all j of xj transpose epsilon. Okay, and what you're going to show in your homework is that this is less than or equal to sigma times a constant times sigma times the square root of log p with high probability. So if I wanted to make this true with probability 1 minus delta, then c would be chosen accordingly. It would depend on delta. But this is true with high probability. The maximum of the absolute value of Gaussians is equal to sigma, which is the I'm sorry. There's a root n here because I forgot the variables had norm n. So it's equal to a constant times the maximum variance of any one of those Gaussians. So what's the variance of any one of these things? It's sigma squared times n because we're assuming the variables have norm n. So it's equal to a constant times the maximum standard deviation of any of those Gaussians times the square root of the log of the number of ones, the number of Gaussians. Something you'll show on your homework. Okay, so we can say that with high probability, probability tending to 1, this is less than or equal to root n times log p times a bunch of constants times this. So let's go ahead and then say that A, in high probability, A is less than or equal to a constant times sigma times root n log p times this. I'm going to use now just the triangle inequality here. It's actually a very crude bound, but doesn't end up mattering. What was B? B was this guy. So now I'm done, actually. Because I can just see, well, what happens if I chose lambda to be this value? So we're going to choose lambda equals this value. If lambda equals this value, then you can see that what I get lambda times the minus 1 norm of beta hat plus lambda times the 1 norm of beta hat. Those two parts cancel. And all I get left over when I sum up A plus B is going to be 2 times this times the 1 norm of beta naught. Right, so then the final bound, our final bound, A plus B, is less than or equal to 2 times a constant times sigma times root n log p times the 1 norm of underlying coefficient vector. And if I were to divide by n, divide this by n, and divide the original mean squared error by n, we'd get this the rate we know, right? Which is the MSE is less than or equal to, 2c sigma root log p over n times the 1 norm of beta naught. So there's the proof of the Lasso basic inequality. It was kind of more like 1.5 boards, although I wasn't really using this board optimally. Okay? The only part we didn't prove is this fact. But this, when you go to the homework, you can use the union bound for that. Do some very basic probability. I think we give you hints too. That's
We did it in 705.
they did. You guys did it in 705. Any questions? So this is a strategy people. Oh, sorry, Kevin. Let me say one thing. This is a strategy people take to prove bounds for the Lasso in general, or not even just the Lasso, but problems in general, where you have smooth part and a non-smooth penalty. Is that we use this fact. It's extremely simple. When you evaluate the loss function or the criterion function at the solution, it's smaller than or equal to what happens when you plug in the population solution, by definition. Then we try to rearrange the loss parts. So we moved this. This is the loss, least squares error loss. We rearrange it so that we have, on the left-hand side, a difference of the losses. And we try to use something like a Taylor expansion to lower bound that by a quadratic between the thing we're estimating the thing we care about. So here it was exact because we had squared error losses. But if we were trying to do this for logistic regression, say, we'd have to do some kind of Taylor expansion to lower bound that by a quadratic. That's where we get this from. On the right-hand side, then, is a difference of penalties times lambda. And there's a term that comes out we call the Gaussian complexity term. It's kind of like this linear contrast that will come out of your Taylor expansion. And so the strategy is similar. I've taken my problem, I've used this fact, I've rearranged it and used a Taylor expansion so that the left-hand side is the mean squared error. The right-hand side is difference in penalties plus a Gaussian complexity term. Take the penalty parameter, large enough so that it dominates the Gaussian complexity term, but small enough that we get a nice rate at the end. That's a very common strategy you'll see in these kind of problems. Kevin, yeah.
I'm still thinking about the fast rate. So when you try to prove the fast rate, you run into a problem where if your design is correlated, then you just can't proceed. Is there any intuition why when we care only about the slow rate, we suddenly don't need to worry about?
Oh, it's a different. They start off similarly, but they go different places. So, for example, this bound is very crude. So what am I using here? I'm using Holder's inequality. All that's telling me is that this inner product is smaller than or equal to the product of their norms. I'm not using anything here about Gaussianity, about epsilon, or about sparsity. This is true for any two vectors, deterministic. So the fast rates, some of them, we'll try to improve on this step. And when you do that, we have to kind of start assuming things about x to make this sharper. That's one place in which they differ. They kind of change some of the steps in different spots. But this is, for example, one thing that's very loose that we know about the basic inequality. Other questions? Okay, let me finish with a result about support recovery. We'll just state it. We won't prove it or anything like that. But the proof is mostly in the notes. Disclaimer is that if you were offended by the conditions we wrote down for fast rates, these are even worse. So support recovery, we're assuming even more than we had to assume, like compatibility and restricted eigenvalue condition. We assume something called the irrepresentable condition, which is even stronger than those. So you'd remember a few things about the Lasso after this class or after the lecture. You remember the hierarchy that, basic result, don't assume anything, we get something that tells us the Lasso can be consistent. The strong results for consistency assume a lot. Support recovery assumes even more. So at that point, it's almost like you're playing a game. I'm not sure that I know of many data sets in real life that satisfy these conditions that we observe. Now, there are data sets that we can produce in compressive sensing that may match this. But I'm talking about observations that you are given, not experiments that you design. So support recovery, I'll just state the result like I said. So we're going to assume the linear model is true, normal errors. We're going to assume that if S is the support of the coefficients, we're going to assume a bunch of things. And here's what they all are. So they're written on page 14 of the notes. We're going to assume something called mutual incoherence. It's also called the representable condition, which is that if I knew the true subset of variables and I were to perform a regression of one of the other variables onto that set, right, this is the regression coefficient if I were to regress xj, these are the regression coefficients if I were to regress xj onto the set of relevant variables, xs, then this has to be small. These have to be bounded away from 1 for all j that are not in S. Okay, so no variable outside of S can align itself too much with the space spanned by the active predictors. That's what this is saying. The regression coefficients have to be small. Now we actually place the minimum eigenvalue condition. The restricted eigenvalue condition and so forth were not explicit eigenvalue conditions. I said you could kind of interpret them as them. But here we actually assume proper eigenvalue bound, which is that if I were to take the eigenvalue of the predictors, but only the active ones of xx transpose xs, then it has to stay away from 0 by some constant. These are our assumptions. This says no variable outside the active set can be correlated with the active set. This says the active set can't be too correlated with itself. And finally, something we call the beta min condition, which says that the true coefficients themselves, when they're non-zero, they have to be bigger than or equal to something. I'm not going to even write down what that is. You can see it in the notes. For all I in S. So this is saying that if we have observed some true subset of variables S, then the coefficients of those variables have to be large. I can't have coefficients for my relevant variables being close to 0. That would be very hard to detect them then, right? So it's like a minimum signal condition. This is a condition on that the predictors can't be too correlated with themselves that are active. Like I said, this is any inactive predictor can't be too correlated with the active ones. So these are much stronger than the other ones. For example, in the consistency results, we made no such, this is new, right? We had to make no such assumption about minimum signal requirements. With consistency, that's true because if a coefficient was small, then it wouldn't really cost to miss it anyways in terms of mean squared error for estimating it, right? Because if it was really close to 0 and we didn't pick it up, then that's fine. But we're going to actually aim now to claim that the Lasso's active set is S. So we're going to have to assume that there's enough of an effect to detect those variables. So here's the result. Yeah, the result says that if all those three are true, and you choose lambda to be bigger than or equal to something like 2 gamma, or on the order of, just write down the order, same as always, root n log p, then we get from the lasso the active set being S. So A hat, or maybe I'll just call it A. This is the support of the lasso solution. We're saying it has to be equal to the support of the underlying coefficients. Then this is true. And not only that, we get the signs right too. So the sign of beta hat A equals the sign of beta naught S with probability tending to 1. So this result came out of the compressive sensing literature. I think it's pretty interesting. One could give an entire lecture about compressive sensing or even a whole course and results like of this flavor. But since the conditions are so restrictive, it's not something that I would actually take with you to the bank when you're doing a data analysis. Right? It's ludicrous to believe that the lasso infinite sample is going to recover, even if the true model is linear, et cetera, the set of relevant variables. You can do simulations to convince yourself that's just not true. The lasso gets things wrong. But there are different setups that we might think about rather than just observational setups where you can design X, and you can also design the signal that you're looking at. And that's what happens in compressive sensing, so that they actually satisfy these conditions with high probability infinite sample, and then you actually would believe that you would get something like this. The last thing maybe I'll close with is just a statement that if all we wanted to do was screen the set of active variables, if all I wanted was to get A contains S, and forget about the signs, and A not being too large, then we can actually do that with much weaker conditions. In particular, we don't need this minimum signal assumption. So there are results on lasso screening that say that if something like this holds, maybe not quite as strong, but we don't have any minimum signal restriction, then the lasso recovers some active set A. It's not too big. In particular, it's smaller than n. Its size is smaller than n. So if p is very big and n is small, then it's not very big. And it's going to contain the set of relevant variables with probability tending to 1. So you might think of it as lasso gets the right variables, probably. It might include some false things as well. Any questions about this kind of stuff or any lasso theory? All right, well, we're going to see you on Monday for the review then. And remember, there's a midterm next week.